A very good morning to all of you. So once again, I cordially invite you all for this engineering thermodynamics course. So in the today's classroom discussion topic, we are going to discuss about the polytropic process and how can we find out the PVT relationships in the polytropic process. So that is the basic idea of having this video on the classroom discussion topic. So what is the motivation? It is essential to know the governing equations of the polytropic process, that is PV to the power of n is equivalent to constant. So that is the governing equation where n is equivalent to polytropic index. And similarly, how can we find out the PVT relationships in the polytropic process? Not only PVT relationships, that is the work transfer, heat transfer, change in internal energy, change in enthalpy. All these things, how can we find out in the polytropic process? These are very, very important one whenever we are solving the numerical problems which are related to the polytropic process. And what is the outcome of this lecture? So the outcome of this lecture is you have to solve the problems on the polytropic process, and you should be in a position to derive the PVT relationships in a polytropic process. So these are the two outcomes I'm expecting from this particular lecture. So I told you that polytropic process governing equation is PV to the power of n is equivalent to constant, where n is known as the polytropic index. Then how can you represent polytropic process on PV diagram? So once again, the polytropic process is represented by drawing a curved line. So this curved line is representing the polytropic process. Then you can have a doubt, sir, isothermal process, adiabatic process and polytropic process. All these three processes are basically representing by means of a curved line. Then how can you differentiate? So that is, the slope value is basically different from isothermal process to adiabatic process and similarly to the polytropic processes. Even though all these three processes are shown by drawing a curved line on the PV diagram, but the slopes are different. That is very, very important one. So P1 V1 to the power of n is equivalent to P2 V to the power of n is equivalent to constant. So that is the governing equation. So now how can we find out the work transfer during the polytropic process? During the polytropic process, because here 1 to 2, it is a polytropic expansion process is taking place. So whenever the polytropic expansion process is taking place, you can start with the minimum, that is the basic governing equation is integration of the PDV, that is the basic governing equation. So here we can have where C is a constant, so that is equivalent to PV to the power of n. So by doing all these particular the substitution, we are able to get the work transfer is equivalent to P1 V1 minus P2 V2 by n minus 1. P1 V1 minus P2 V2 by n minus 1, or P2 V2 minus P1 V1 by minus n plus 1. So it is somewhat difficult to remember. So that's why I am multiplying with the minus sign on the numerator side as well as on the denominator side. So P1 V1 minus P2 V2 by n minus 1. So that is the work transfer during the polytropic expansion process. So how can we find out the heat transfer during the polytropic process? So the heat transfer is always, because it's a very, very important equation, the change in the heat transfer is equivalent to how many times of the change in the work transfer. That is gamma minus n by gamma minus 1 times of the work transfer is equivalent to change in the heat transfer during the polytropic process. So just now we are discussing about what should be the n value for the various processes. So whenever n value is equivalent to 0, because whenever you are substituting n value is equivalent to 0, so v to the power of 0, that is nothing but 1. So P into 1 is equivalent to constant. So that is a constant pressure process. So for constant pressure process, n value should be 0. And whenever you are having the 1, n value is equivalent to 1. So PV to the power of 1 is equivalent to constant. So PV is equivalent to constant. So that is nothing but the isothermal process. For isothermal process, n value always equivalent to 1. Then for the adiabatic process, n value should be equivalent to gamma. So PV to the power of gamma is equivalent to constant. And similarly here we are able to have for the isochoric process, n value should be infinity. So then like that we can differentiate the various processes based upon the polytropic index. So whatever the things so far we have discussed, the same thing this is labeled here. So during the polytropic process, n value should be equivalent to n only, because PV to the power of n is equivalent to constant. and it is the formula for the work transfer, P1 V1 minus P2 V2 by n minus 1. And the delta Q, I've already told you that gamma minus n by gamma minus 1 into the work transfer. The PVT relationships, so here you can observe the important point here between the adiabatic and polytropic processes. Gamma is to be replaced by n. That is the only difference between the adiabatic and polytropic. So just you can see P1 V1 to the power of gamma is equivalent to P2 V to the power of gamma. So just you replace gamma by n. So P1 V1 to the power of n is equivalent to P2 V to the power of n. So that is gamma is replaced by n. So similarly, the second pivot relationship and the third pivot relationship also. So T2 by T1 is equivalent to P2 by P1 whole to the power of n minus 1. So like that, we can have the pivot relationships of the polytropic process. So similarly, now you can see some gate questions based upon the polytropic process. 1 kg of the ethane gas is compressed from 1.1 bar 27 degrees centigrade according to a law PV to the power of 1.3 is equal to constant. That is, how can you identify a problem, whether it is a constant volume, constant pressure, constant temperature, adiabatic or polytropic? How can you identify? So based upon only this important one, that is a PV to the power of 1.3 is equal to constant. So PV to the power of 1.3 is equal to constant means is the PV to the power of n. It is resembling like PV to the power of n, where indirectly has given n value is equal to 1.3. That is a polytropic expansion value. Polytropic index value as given as 1.3. Until the pressure is 6.6 bar, calculate the total heat flow to or from the cylindrical walls. So he has given the molecular weight of the ethane is equivalent to 30, that is the C2H6, and similarly the specific heat at the constant pressure value also he has given. So I told you that first of all it is very important to find out the characteristic gas constant of any gas. So R is equivalent to RU by M, and you know that RU is always 8314 joules per kilomole Kelvin, and the molecular weight he has given as the 30. So the R value of the ethane is 277.31 joules. Now you convert into the kilojoules. It is 0.277. And now Cp minus Cv is equivalent to R, you know. So Cv is equivalent to Cp minus R. So find out what is the value of the Cv. And you know that gamma adiabatic index is nothing but it is a ratio of two specific heats Cp by Cv. So gamma is equal to 1.888. So from this, just you can make use of the pivot relationships. With the use of the pivot relationships, find out the final temperature value T2 is equivalent to 453.6 Kelvin, and make use of the work done equation. So P1 V1 minus P2 V2 by n minus 1, where PV is equivalent to RT. So R into T1 minus T2 by n minus 1, substitute all the values. Work done is equivalent to minus 141.8 kilojoules per kg. Then you find out the heat transfer, gamma minus n by gamma minus 1 into work done. Substitute all the values, you are able to get 84.5 kilojoules per kg. So like this, you can solve n number of the problems on the polytropic process. I hope you understood the basic concepts of the polytropic process, that is what should be the n value, how can we find out the pivot relationships, work transfer, heat transfer, internal energy, enthalpy, and all these things during the polytropic process. So thank you very much for attending this particular lecture. Let us meet you once again in the next lecture. Thank you one and all.